Thanks so much for joining me this evening. My name's Nathan Roth. I'm a member of the investigation team for the Double Asteroid Redirection Test, or the DART mission. And this was NASA's first planetary defense test mission. Tonight, I'm going to give you some background and some motivation for the DART mission. I'm going to walk through our primary mission objectives that we wanted to meet, and then I'll share with you some videos and some photographs from the mission itself, provide some of the first results, the things that we've learned, and give you an idea of where we're going forward from here. So the DART mission falls under our wider umbrella of a planetary defense strategy, which has multiple components. We want to search for, detect, and track objects in space that may be hazardous to the Earth. We call these near-Earth objects, or NEOs. Once we've found an NEO, we want to characterize it. We want to understand how big is it? What sort of orbit does it follow? Will it ever pose any potential hazard to the Earth now or in the distant future? We want to plan and coordinate. We want to develop strategies that we can use to deal with in the event that we are ever faced with a hazardous near-Earth object. We want to develop strategies and exercises where we can mitigate the risk posed by a hazardous NEO if one is ever discovered. And then we want to assess. We want to learn what went well and what went wrong in our mitigation exercises and improve on our techniques in case we ever need to work to defend our home. And the DART mission fell under the mitigation component of this planetary defense strategy. So DART was meant to be the first demonstration of the kinetic impactor technique. So we have multiple different techniques in our planetary defense portfolio that we can use if we need to try and mitigate the hazard posed by a near-Earth object. For the DART mission, we wanted to demonstrate the kinetic impactor technique, where we collide a spacecraft into an asteroid to shift its orbit, moving it away from an orbit that poses a hazard to the Earth into one that no longer poses any danger. And we have a very good motivation for wanting to think about this sort of thing. This is a map of the globe showing you fireballs or asteroid impacts on the Earth measured by US government sensors between 1988 and 2023. The larger and brighter the circle that you see, the more energetic the impact event and the larger the asteroid that caused it. The biggest one here in red, you might recall reading about in the news back in 2013. This was the Chelyabinsk impact over Russia, and it was caused by an asteroid about 20 meters in diameter, and it caused an explosion equivalent to about 500 kilotons of TNT. Another historic example that you may be familiar with is the Barringer meteor crater in Arizona. This was formed about 50,000 years ago by an impact from an asteroid that was about 50 meters in diameter. It created a crater that was over 1 kilometer across and about 180 meters deep, and it caused devastation for tens of kilometers around the impact site. And if you were to superimpose this impact zone over a crowded urban area, such as, say, the Washington, D.C. area, you can imagine the sort of effects that would happen if such an impact occurred today. And we can further break down the sort of hazards posed by near-Earth objects by the numbers, by the size of the asteroid, how often we expect a given asteroid size to impact the Earth, the effects of such an impact, how many of these objects we think are in near-Earth orbits, and based on statistics, how many of them we think that we've discovered. On the smaller end, we expect asteroids that are about 4 meters in size to impact the Earth about once per year. We think there are about 500 million of them in near-Earth orbits, and we've only discovered less than 0.1% of them based on statistics. However, if one of these does impact the Earth, you probably wouldn't notice much. There would be a brief bright flash. There could be some meteorites that are left on the ground, but otherwise you'd go about your day without ever knowing it had happened. On the other hand, on the largest end, an asteroid up to 10,000 meters in size is expected to impact the Earth about once every 100 to 200 million years. It would be catastrophic to life as we know it. However, we only think that there are 4 of these in near-Earth orbits, and we have discovered and are tracking all of them. Now, as the asteroid size increases, on the one hand, the severity of the effects of an impact increases. However, the number or the frequency of impacts that we expect decreases. The number of asteroids that we believe are in near-Earth orbits for a given size decreases, as size increases. And thankfully, our discovery statistics, where we know about these asteroids, we can track them, and we can plan for any hazards they may pose, steadily get better and better. And so with all of this in mind, we chose the ideal target for DART, NASA's first planetary defense test mission. It's the binary asteroid system Didymos and Dimorphos. Didymos is the larger asteroid you see in the center, and Dimorphos is the smaller asteroid orbiting it, almost like a small moon. For the DART mission, we collided a spacecraft with Dimorphos, the smaller asteroid. Before impact, a small satellite, Leisha Cube, jettisoned from the main spacecraft and photographed the impact of the event. Now, the force of the impact altered Dimorphos's orbit around Didymos, thereby demonstrating the kinetic impactor technique. Now, what's important to note is that these asteroids never posed any hazard to the Earth. Before the mission, they were in a perfectly safe orbit, and there was no chance that the impact of the mission could have knocked them into a hazardous orbit. And I can confirm to you now that they are still in a perfectly safe orbit and pose no hazard to anyone on Earth now or in the future. Now, to put some of this into scale, I wanted to show you these asteroids alongside some landmarks that you may be familiar with. On the one hand, we have Didymos, the larger asteroid, and it's about 780 meters in size. This is comparable to skyscrapers such as the One World Trade Center or the Burj Khalifa. The smaller asteroid Dimorphos, which DART collided with, is about 163 meters in size. And so this is around the size of the Statue of Liberty or perhaps the Great Pyramids. Smallest of all was the DART spacecraft itself, about 19 meters in size, so something like a large school bus. Now, DART's level 1 mission requirements, the objectives that we had to complete in order for the mission to be considered a success. First, we had to impact the smaller asteroid Dimorphos with a spacecraft in around September or October of 2022, when it was relatively close by to the Earth. Second, we had to change how long it takes Dimorphos to orbit Didymos by at least 73 seconds. Third, we had to measure the change in the period that the impact caused with high precision, using ground-based observations with telescopes here on Earth before and after the impact. Finally, we had to characterize the impact itself. What sort of material are the asteroids made out of? How big of a crater did we leave? How much ejecta, or dust and rock, were thrown into space by the force of the impact? And how much momentum was transferred from the spacecraft to the asteroid by the force of the collision? We conducted the test at the ideal time. So in the center here, you can see the sun. The Earth is orbiting around the sun in blue, and Didymos is orbiting around the sun, shown in white. We launched the DART spacecraft in November of 2021, and we timed the impact such that it would occur in the fall of 2022, when Didymos was only about 7 million miles away from the Earth. With it being that close, we would be able to maximize our sensitivity using telescopes here on Earth to measure the impact and its effects. Additionally, having the target so close would make it easier for us to communicate with the DART spacecraft. However, again, this was many millions of miles away from the Earth, and the impact caused no risk to anybody here on the ground. And so this is a picture from the launch date on November 24th, 2021, when a Falcon 9 rocket carried the DART spacecraft into space and towards its collision course with Dimorphos. Impact was on September 26, 2022 at around 7 o'clock in the evening Eastern Time. And I'm going to share with you some video, both from the final moments of footage beamed back from the spacecraft and also from mission control just before impact. So here in the center, you see footage from the spacecraft. This is Dimorphos and this is Didymos, and it's steering towards the asteroid. Now we're moments before impact. Dimorphos takes up the entire field of view, and then the feed cuts off as we achieve impact. And like a lot of the folks that you see in this video, I was actually up at APL that night with other team members watching the live feed from the spacecraft being beamed down to Earth, seeing the asteroids come more into focus and get larger and larger in the field, and finally seeing the feed cut off as we had achieved impact and a successful test. And it was an incredibly exciting night to be a part of. Now, one of the things that we had to demonstrate with this mission was the ability to autonomously navigate a spacecraft into an impact with an asteroid. Because of the large distances between the Earth and a potentially hazardous near-Earth asteroid, it takes significant time for communications from Earth to the spacecraft and back to traverse the great distance. And so it's really not possible for somebody to be sitting in mission control on the Earth, actively steering the spacecraft into an asteroid for this kinetic impactor technique. Instead, we had to develop and show the feasibility of a technology for the spacecraft to use its own computers to acquire the asteroid when it was far away and continuously alter its trajectory, steering it towards the asteroid and towards a successful impact and kinetic deflection. And so this is footage from the spacecraft in the final 5 minutes before impact. In the center here, you see Dimorphos, and over here you see Didymos. And the footage is jostling back and forth as the spacecraft adjusts its trajectory and hones in on the target Dimorphos. You can see more and more features coming into focus on Didymos, the larger asteroid, and now Dimorphos is starting to dominate the field. You can see the large features on the surface, and then in the seconds before impact, you can start to make out rocks and boulders and pebbles. And finally, the screen goes red at the moment of impact and a successful test. To give you just a little bit more of a slower view of the scale of these two asteroids relative to one another, this is 2.5 minutes before impact. And you can see Didymos here on the right and Dimorphos, the target of the impact, over here on the left. And now to show you Dimorphos in a little bit more detail, the smaller asteroid which DART collided into. 11 seconds before impact, when the spacecraft was 42 miles away from Dimorphos, you can see the overall shape of the asteroid. You can see the large and impressive features of different rocks on its surface. And now, only seconds before impact, when the spacecraft was just 7 miles away and this entire field of view is only 100 feet across, you can see in fine detail the boulders and the rocks and the pebbles strewn across its surface. And it's just incredible detail. As somebody that's been working in this field for a while, studying bodies like this, comets, asteroids, other objects in our solar system, I want to try to convey to you how special an image like this is. It's so rare that we get to send a spacecraft to another world in our solar system. It really only happens a few times within your life. And to be able to see another world in this much detail, this sort of exquisite precision, it's really something special. And I hope that I can convey to you just how important these images are, being able to learn about the surface of these asteroids. And like I mentioned earlier, just before impact, a small satellite jettisoned from the main spacecraft and then flew along to photograph the results of the impact. This was called LISA-Cube, and these are some of the photos that it took in the moments after impact. You can see Didymos here in the center, and up near the top, you can see the spectacular plume of ejecta, the dust and the rocks that were spewed into space by the force of the impact. And then as LISA-Cube flew past the asteroids onto the other side of them, you can continue to see Didymos and then Dimorphos and the ejecta, where Dimorphos is the small body here in the lower left, and you see this incredible plume of ejecta spewing out from the impact site. And here in this particular picture, I've enhanced the ejecta to where you can see in each square, we've bumped up the contrast, and you can see all of these amazing filaments and streams of dust and rock that were thrown into space by the force of the impact. And this is really exciting to scientists because by analyzing the shape of this ejecta, understanding how much dust and rock is contained within this ejecta, we can better understand what the asteroids are made out of. We can better understand the physics of the impact, and we can better plan and refine our planetary defense techniques in case we should ever need to use them in a real planetary defense event. Now, in addition to the Leisha Cube satellite that flew along with the spacecraft, we organized a worldwide observing campaign of telescopes here on the Earth and in space to monitor the asteroids before and after the impact. I'm going to show you just a few of some of my favorite videos and images from all of these observations. There are many, many more, and I would encourage you to look them up. So this is a video from the Las Cumbres Observatory in South Africa, and you can see before impact and then in the moment of impact, this spectacular plume of ejecta that rockets away from the asteroids. We were able to capture the impact and its after effects with a telescope on every single continent, including in Antarctica. And beyond Earth, we also leveraged our space-based assets, using both the Hubble Space Telescope and the James Webb Space Telescope. And so this is a video of the James Webb Space Telescope observations from pre-impact to about 5 hours post-impact. And you can see all of the dust and rocks spewing out from the asteroid in a dramatic fashion. Similarly, at different wavelengths, the Hubble Space Telescope was able to monitor the impact as well. And you can see how the ejecta evolved from Hubble's point of view from 22 minutes to 5 hours to 8.2 hours post-impact. And one of the really spectacular things that happened in the days and weeks afterwards was being able to watch the way that the ejecta evolved. So initially, we just had this cone of ejecta emanating out from the crater and the impact site. But in the days and weeks that followed, radiation pressure from the sun stretched the ejecta out into a long tail, almost like a comet, tens of thousands of kilometers long. And we were able to watch the evolution of it, both from the ground and in space. And so in this particular set of observations, about 64 days post-impact, the total field of view is 32,000 kilometers across. So you can imagine the scale of this tail of dust and ejecta coming out from the asteroid. And by understanding how this tail evolved and changed with time and how much material is contained within it, we can learn more about the asteroids, what they were composed of, and how we affected the system with the impact, and better refine our planetary defense techniques. And on October 11th, about 15 days post-impact, NASA officially confirmed that the DART mission had successfully altered Dimorphos's orbit around Didymos. For the first time as a species, we had reached out and changed the way that an object moves through our solar system. And to give you a little bit more of the final numbers, again, I'm showing you a diagram of the Didymos and Dimorphos system. Pre-impact, it took Dimorphos 11 hours and 55 minutes to orbit Didymos. We call this its orbital period. Now, on the day of the DART impact, the DART spacecraft collided with Dimorphos. The force of the impact caused Dimorphos's orbital period around Didymos to change. You may recall that I said our base mission requirement was changing its orbital period by at least 73 seconds. Its new post-impact orbital period is 11 hours and 22 minutes. So we changed its orbital period by 33 minutes and had an enormous successful demonstration of the planetary defense technique. And I want to show you just briefly how we understand how the orbital period changed. So this is a diagram showing you how the brightness of these asteroids measured from Earth changes as they rotate and orbit one another. So the sun is off here to the left. This blue line is the direction of the Earth, and you can see Dimorphos orbiting Didymos. As Dimorphos passes through Didymos' shadow, you get this dramatic drop in brightness. And similarly, as Dimorphos casts its own shadow onto Didymos, you get a smaller drop in brightness. And so by measuring how deep and how widely separated these dips in brightness are as the asteroids move into and out of one another's shadow from our perspective here on Earth, we can work to understand the original orbital period and just how much the orbital period of Dimorphos changed after the impact, and we can gauge how successful our test was. Now, one of the things going into this mission that we were unsure of is just what exactly Dimorphos was made of and how it was put together. Was it a very hard, rocky, and solid object, almost like, a slab of granite? Or was it instead a bunch of rocks that were more loosely held together, like perhaps a rubble pile? And depending on that, we would expect different amounts of ejecta. In the very hard, solid case, we would expect almost no ejecta at all. And then if the asteroid was more loosely held together, we would expect a greater and greater degree of ejecta. And from our measurements, we feel that we fell somewhere in between the some ejecta and the lots of ejecta scenarios. And by measuring this, we're able to gain an understanding of just how much momentum the spacecraft transferred to the asteroid. We're able to learn about the structure of the asteroid, and we're able to better understand what we need to do in order to change an asteroid's orbit by a given amount, if we should ever need to do so in the future. Now, the overall mission of planetary defense is far from over. DART kicked it all off in 2022 in the fall when it first impacted Dimorphos and changed its orbital period around Didymos. There's a follow-up mission being sent by ESA called the Hera mission. It's going to visit the system in 2026, and it's going to spend months characterizing the after effects of the DART mission. How big is the crater that was left behind? What are the long-term effects on the overall system itself? And we want to be able to get this key data to develop asteroid deflection into a well-understood, scalable, and repeatable technique. Finally, I would encourage you to learn more about the DART mission and about our planetary defense efforts. You can visit the DART website to learn more about the background of the mission and the results that we're finding. You can join the planetary defense community, and I encourage you to follow any of our social media handles on Twitter, Facebook, or Instagram. There is still so much work being done on the DART mission. There's so much data to analyze. There are still follow-up observations being conducted right now. We're still learning so much, and there are updates being posted all the time. So I encourage you to look into them and to continue following this first chapter in planetary defense. And with that, thanks so much for joining me this evening.